Hello everyone. So today we are going to welcome. I welcome you all to the revision series of business uh, basic digital system. So today we have with us Prathamesh, who is currently the TA also. So he will be covering your doubts and give you some important tips to for the quiz one. So Prathamesh, you can proceed from here.
Okay, Abhishek. Am I audible to everyone?
Yes, yes,
Yes,
you
yes.
are.
Uh, Please don't call me sir. I'm just like uh, your friend here. Uh, so you can like talk me with my name. Let me share my screen. Can you see my screen?
Yeah.
Uh, so here onward, if you have any doubt or anything, you just turn on your mic and speak because I won't be able to see your comments and emojis either. Okay.
Yeah,
Uh,
Prathamesh, I have a doubt in week one VTC graph equation actually. In that topic, I didn't understand like what is happening in between that. Like sir has taught not like the upper
uh,
region is logic zero, I guess, and the lower one is the logic one. So I
okay, I
wanted to
will
know.
explain.
Yeah,
So, what I am thinking about is we will cover one week's content, and then I'll ask about doubts. If you have any, you ask them, and I'll answer. Okay.
yeah,
Uh, so one another thing that I spoke with instructor. So there is another revision session tomorrow, right? By instructor. Uh, so they have told me to cover initial topics and they'll be focusing on the later week 3 and week 4. Okay, I'll try to cover week 4 as well, but still, my main focus will be first 3 weeks. Is it okay with everyone?
yep.
Okay, so we'll start with the week 1. So, uh, so in week 1, we start with understanding how we represent the logic 0 and logic 1 in terms of voltages. Okay, so uh, to do all the things we do with all the digital systems, we have to represent the logic 0 and logic 1 in voltages, and it is like very straightforward way to do so. Uh, we represent logic 0 with 0 volt and logic 1 with uh, high voltage. It might be 1.5 in some cases practically 5 volts. Here we will consider it 5 volts. Okay, so if you take a basic inverter, so this is an inverter. If you give it 1, it will give you 0. If you give it 0, it will give you 1. Okay, so what is happening on the voltage level? One, just as we said, it's 5 volt. If we are giving 5 volt as input to this logic gate, the output here should be 0 volts. Okay, and if we give 0 volt as input, the output should be 5 volts. So if this thing, if we want to represent in a graphical way, we can do it. Uh, so this is going to be our V output, and this is uh, going to be our V input. So now tell me, when the input logic, suppose this is 1, 2. So now tell me, somebody tell me, if the input is 0 volt here, okay, here, if it is input is 0 volt, what should be the output?
5 volt.
Yes, output should be 5 volt. And if the input is 5 volt, what should be the output?
0 volt.
0 volt, which will come here only. But you can see that this thing is not at all practical, because in reality voltage can vary anywhere in between. Okay, so what we want is that till certain limit, let's say here at 2.5, we will consider this region as low and this region as high. Okay, same is true for the output. At around 2.5, we will consider this below region as low and the upper region as high. So now what should be the characteristic of this gate is like this. Until 2.5, uh, the output should be exact 5 volt. I am unable to draw a straight line here. And after, until it's from 0 to 2.5, the output should be 5 volt strictly, and after 2.5 the output should be 5 volt, right? Anybody does have any doubt in this thing? Hello?
No, sir.
No, no, sir.
But can you can see that this thing is good in theory, but this thing won't exist in practice, right? Also, one thing, suppose our input is here, okay, somewhere here, somewhere. Suppose our input is somewhere here at around 2.5, okay, and we are transmitting this voltage through a wire, and somehow, maybe by some signal, outside signal, some electromagnetic field, it just increases little bit and becomes 2.6. What will be the output then? The output will be 0. Even though the input initially was lesser than 2.5, the output will become 0, and it will be actually false output. It will be incorrect output. So we also want some area where uh, if the input come if there will be any noise in the input, that noise should be tolerable. And also this graph is not practical at all. In real life, there won't be these edges. These are non-practical. So what we do then, that we say uh, so what we see in real life, not even in real life, and even also in theory, we say let there be some voltage till we will consider it as voltage high, then there will be some transition period which will act as a kind of a barrier that will prevent the logics from mixing. Uh, so this becomes the VTC that we have studied in the lectures. So any doubt till this point, guys?
No, sir.
No, I mean, all clear.
So so uh, you got this VTC. Why we have this region which is all considered as high, and then this region which is not considered in logic terms, and then this region which is considered low. Okay, so if uh, in this graph now we can define some terms. So in case of input, what we can say that there is this voltage here somewhere, and then there is this voltage. Any voltage that is in this range will be considered as voltage logic low. Okay, this will be considered as logic low. Any voltage in this range will be considered as logic high. Okay, so what we can do that we can define these, we can give some names to these two voltages, because 0 and 5 is defined by the power of the circuit, but these two are kind of arbitrary. We can change these two points. So this point is named as VIL, voltage input low. Any voltage that is below this VIL will be considered as logic low at out input. Okay, this I and L, and this voltage here is VIH. Any voltage that is higher from this point will be considered as logic high. Exactly the same thing we discussed, and the same thing from which we made this graph. Just we are giving them formal names. Okay, same thing is here in the output. This the y coordinate, which is V out of this point, can be termed as VOH. Voltage at output that is considered high. Any voltage, sorry, this should be 5 here. Okay, that is at 5 volt will be considered as logic high. And similarly, the y coordinate of this point will be considered as uh, VOL. In any voltage that is below this level, which is around 0 in this term, this case, will be considered as logic low. So these four definitions we have created just to convey all the information that exists in this graph. So any doubt in these VOH, VIL? Anybody has any confusion or doubt in these terms, guys?
No, sir.
So everybody understood the VOH, VIL, all these terminologies. Okay.
Yes, sir.
So now, uh, as written here, so this is the graph part of the VTC. Okay. Uh, these values can change, but because this VTC is of inverter, this will stay constant. This uh, the shape of the graph will be always a Z. And important thing that the first region here has some logic output related to it. Also the third region, but the middle region does not have any logical output related to it. So if voltage is in between these 2 points here, this point and this point, the logic output will be not defined. Okay, unless until you get specifically mentioned, like for example, there will be some, might be some questions where there is some voltage for which logic 1 is defined, then there is some voltage for logic 0 is defined, and for in between they say it's logic zero point 0.5. Okay, unless until anything like this is mentioned, this is not defined. Okay, so any voltage in this range will not produce any logical output. But we can use input voltages or output voltages to derive the corresponding input output voltage. Like uh, they can give you like at 2 volt what is the 2 volt, what is the output. So you can calculate the output by finding the equation of this line, and you can find the equation by these VOH and VIL. So basically I will write it here. For this point, the x coordinate is VIL and the y coordinate is VOH. Okay, and for this, the x coordinate is VIH and y coordinate is VOL. So this thing is very important, and this makes the whole VTC concept very simple. So now we will see this equation part. Okay, this equation part, and this equation part is strongly related to small signal analysis. So suppose like there exists this IC named 7404. Have anybody heard or used it? 7404.
Yes,
I
sir.
guess. So this is an inverter, right?
Yes, sir.
So if you go on net and search for this inverter's datasheet, you will get all these VIH, VIOL. Okay, but if you will see the graphs won't have these edges we were saying. Graphs won't have these edges. Okay, why? Because in uh, practically the making those edges is like almost not possible. Okay, uh, so what happens in real life? In real life, there will be always some curve to those edges. So this is VO and this is VI. Okay, so what will happen in reality? In reality the VTC will look like this. It will be it will be straight till some point, and then it will curve. It will go down, and it will again will have something like this. Why? Because creating those edges is not possible in reality. So these graphs can be represented with equations. Let be some f of vi. Okay, most time it is if you know these kinds of functions, some a divided by 1 1 plus e raised to plus or minus, I forgot right now, but raised to power some a v plus b d p plus b v in. These functions exist in these formats in real life. Okay, so now can anybody tell me how can we define those edge points, those corner points that we have defined here in the graph, in these continuous graphs which do not have any corners? Do anybody have any idea about it? Guys, if you have any idea, please speak. Does anybody have any idea? Okay, you have seen the small signal analysis lecture, right? By Prof. Guys, am I audible?
Yeah.
Yes, sir.
Uh, So, what I'm saying, if you go and see in the small signal analysis lecture, Professor has told how we can define these VIH, VIOL in in these curves where uh, there are no corner points. So, what we can do is see what we want from these points. Why we defined those points at the first place. I told you why did we define those points. So can you tell what I have told just now? Why did we define those corner points? Why are these corner points are important?
For VIL and VIH points, actually.
Why did we define them? Like why what is the purpose of those points? See what we
Sir,
did.
I think due to where the क्या कहते हैं, I think
You can speak in Hindi.
सर इसलिए हम इन पॉइंट्स को कंसीडर कर रहे हैं जैसे कि हम इनपुट अगर लॉजिक जीरो दे रहे हैं तो किस वैल्यू तक वो लॉजिक हाई ट्रीट होगा इस कारण से।
Yes, we are using them to define the regions, and also one specific property of these points that if there is any noise in the input or output, that should be reduced. Therefore we have defined this whole region as high rather than just 1 point of 5 volts, right? So in the same way, if we analyze, if you see the in the lecture, professor has analyzed these equations, these curves, and came to the conclusion that if the gain of this circuit is -1, if gain of this whatever gate we are using is equal to -1, what will happen? That the input won't attenuate because the gain is modulus of the gain is 1, and because it is negative, if any change, any small change will happen, some delta v, small delta v, suppose small change will happen, the gate will try to reduce it because this negative sign by small delta v. Okay. So what is gain? Gain is just v out by v in. And in this case, it will be derivative of v out with respect to v in. Okay. Whenever this derivative will be equal to -1, those points will be are defining VIH, VOL points. In this graph, if you see what is V dVo by dVi, can somebody tell what is dVo by dVi, which is the gain in this graph? Think about it. What is dVo by dVi? Can anybody tell? Guys, please speak. How can I like teach you if you are not speaking?
सर आई
It
थिंक
is
इट इज अ गेन।
slope of the
Yes,
graph.
correct. It's slope. dVo by dVi is just the slope of this curve. Wherever the slope of this curve will be -1, those points are these points that we have seen in this graph. You got my point? So if you get any equation like this, I guess there was one question at my time about, based on these kinds of equation. What you have to do, you have to differentiate this equation with respect to Vi, and then see wherever the curve gets becomes sorry slope becomes -1. Those points will become our VIH, VIL like depending on their position. Okay, you get this point?
Yes, sir.
Yes, sir.
Yeah. Yes, sir.
So do you have any doubt in VTC till now?
No, sir.
No, sir.
So somebody was saying that didn't get it. So did you get it? Hello?
Yes, sir.
Some you got it right. If you have any doubt, you can ask. Any doubt? Okay, we'll go ahead. So okay, noise margin. So we are saying wherever the gain will be -1, those points will become our VIH, VIOL respectively. So where we are defining these points based on noise because we want to reduce the noise. So can someone tell me what is noise margin in this context? Can somebody tell me what is noise margin in this context?
Amount of noise allowed so that the answer does not changes.
Correct. So, tell me, will there be one noise margin or there will be two noise margin for an inverter?
One noise margin.
Yes, will there be one noise margin or two noise margins?
I think one noise margin.
Okay,
I
so
think two.
let's draw a different two. So tell me why one or why two? Those people who have said one or two, how do you think like why one or why two?
Sir, I think it is one
Two.
as it is
Mhm.
taking one input. So,
Okay, you are thinking because there is just one input, there should be one noise margin. And
yep.
who the person who said there are two noise margins, what is your logic behind it?
I think there must be two margin because one is for lower value, that is up 0 volts, and one is for 5 volts higher value. So one should have means एक में थोड़ा सा ज़्यादा वैल्यू ऐड करनी पड़ेगी, एक में थोड़ा सा कम वैल्यू लेनी पड़ेगी ताकि उसको
Hmm.
उसी को नॉइज़ कंसीडर किया जाएगा। क्योंकि अगर फॉर लोअर वैल्यूज़ अगर ज़्यादा भी बहुत नीचे जा रहा है तो भी एक्सेप्टेबल है क्योंकि उसको 0 ही लाना है, ऐसा है केस।
Hmm. So let's draw a different graph here. Okay. Uh, so here we are just going to consider one axis only. So uh, this is voltage. Okay. Uh, this is voltage. Let's consider input. Okay. So suppose there are two gates uh, cascaded one after other. Okay. So this will produce some output and this will take it as input. Okay. So let's say the output of this gate is low right now. Okay. The output of this gate is 0. This should get 0 and should produce 1. Okay. So how we'll see it in terms of voltage? The output is somewhere here low. Hmm? Suppose what happens that there comes some noise in between and this value changes to some higher value. So what we want that whatever the logic output of this gate, the same logic value should be input of this other gate. If this value is let's suppose even higher, some high noise came, and if this kind of situation happen, then what will happen? This output of this gate will be 0, but this gate will get input as 1. So this is exactly what we do not want. So what is noise margin here? The amount of margin that this, suppose this is noise margin. What is this? This is the difference between what is the output of this gate, the voltage of output of this gate, that is considered as logic 0. In the above we said it's 5, sorry, output 0 is 0 almost here. I have not drawn it correctly, but it should be 0. Output of this should be, this gate should be completely 0, but this gate, the other gate that is taking input, that will consider the range till this VIL. Any input in this range will be considered as 0. So this whole area is our noise margin. But see what we are doing. We are doing it for just one logic value 0. As somebody said, there should be two noise margins because there are uh, two logic points we are considering, 0 and 1. One noise margin for logic 0 and one for logic 1. So basically what is happening here, whatever this gate is outputting, the same value, logic value, should be input at this other gate, but there can be some noise in between. So the difference between what this gate is considering as V output low and the this gate's input V input low, the difference in these two values will be noise margin low. Uh, Somebody raised your hand. You can speak. Uh, any doubt? Guys, I won't be able to know if you raise hands and comment. Okay, so you have to speak directly. It's okay. Is my explanation of noise margin low graspable? So can you get? Are you getting what I'm saying?
Yeah, yes, sir.
So now if somebody explain me what will be noise margin high. What will be noise margin high? Can somebody explain? You have seen what noise margin low is. It is just the difference between what is the output of the previous gate that is considered as logic low and the input, the voltage input that is considered as logic low. The difference in those two, this region is noise margin. Any noise in this region will get rectified by these gates. By speak. Any doubt in this? Hmm. There are 22 people. No doubt. Okay, I'll go forward. So what is noise margin high? Again, same way. Whatever is the V output high and whatever that is V input high, the difference in these voltages is noise margin high. Are you getting my point?
Yes.
So the formula will be uh, I guess you have seen this VIL minus VOL is noise margin low. You have seen this formula, right? Is the formula correct?
Yes.
Yes, sir.
Uh, so, but the V high, we do VOH minus IH. The reason is this term is going to be higher than this term. So the noise margin should be always positive. Okay. So what you can do, you can always you can sub subtract any value like VOL minus VIL and just take mod of it. So it will become positive because the difference will be uh, won't change by turning them. You just take mod of it, or you can use these also. I won't confuse you at the last moment. So you can use the formulas given. This is noise margin high. Okay. Same way. Basically,
Yes.
the noise margin is for uh, preventing noise from corrupting the signal. Okay. That's the purpose of noise margin. And the reason there are two noise margin because there are two states, low and high. Noise margin that is the margin of noise that won't affect the low. The low will remain low, and the high for that when the high is for when high will remain high. Okay, so should I go ahead, or
Yes, sir.
because this is all what week one has. Any doubt in week one?
No, sir. All clear.
All clear. So let's see what is in week two. Okay, week two is all binary conversion and to 8-bit. Sorry, not 8-bit. Base 8, base 16. One's complement, two's complement, sign magnitude, and all. Okay. Uh, so you understand basis, right? What is a base? Like we use decimal system. That is basically we use decimal system, which has base 10, and computer use binary system, which has base 2.
Yes, sir.
Yes, can somebody tell me what is this whole thing base 10, base 2? What does it mean?
So like it has number from starting from 0 to 9,
Hmm.
and the binary means that it takes only two number, that is zeros and ones,
Hmm.
and that hexadecimal starts from 0 to 9. Then we have A B C D till F, sir.
Uh-huh. So these are all the symbols. Okay, symbols. These are all just symbols that we use uh, to we use to indicate the number. What is much more deeper meaning of base? Like, what do we mean by base 2 or base 8 or base 10, 16? What is uh, like deeper meaning of these terms? Can anybody tell? Okay, I'll go ahead. So let's see. Let's take one number. My three digits in my 625. Let's take these three digits. Okay. Uh, what is what these three digits are in base 10. So, what is meaning of that these three digits and are in base 10? Because these three digits can also in base 7, can they? Right? These three digits can also be in base 7, base 8, and any higher base that is larger than base 7, this number can be there, right? Are you getting my point? This number can exist in any base that is higher than base 7.
Yes, sir.
But see what will happen. The meaning of this number, if you take stones and pile them up according to this number, the piles will be very, very different in different bases, right? If it is base 7, it will be the smaller pile. But if it is base 16, it will be much bigger file. Why? Can you see like the direction I'm pointing? The same number can exist in different bases, but the meaning of this number will change with base. Okay, I'll go ahead. So, uh, this base thing exists. Does this base thing exist in Roman numerals? Have you ever thought about this? I I will always be 2. It is fixed, isn't it?
Yes,
Yes,
sir.
sir.
There is no meaning of base in Roman numerals. It exists only in the normal numbers we use. Why? Because Roman numerals are not place value system. The numbers we use are place value. Place value. Meaning of this number depends on the place they are holding. So this is very different from this, which is very different from this. If you apply Roman logic, all these three numbers are equal, because in Roman it is 6, it is 6 plus 0, which is 6 again, and this is also 6 plus 0 plus 0, which is also 6. But they are not equal in place value system, because this is 6, this is 6 into 10, and this is 6 into 10 square. And what is 10 here? 10 is the base of these numbers. So what is base? Base is, for example, in this 6 to 5, if it is base 7, this in base 7 actually means that it is 6 into 7 square plus 2 into 7 raised to power 1 plus 5 into 7 raised to power of 0. This is base. The value of that place, the value by which we measure of, of that place is the base. If it is base 10, this will become 10 square, 10 raised to power 1 and 10 to the power 0. In binary, again 1010, it is 1 into 2 cube plus 0 into 2 square plus 1 into 2 plus 0 into 2 plus 0. So you get what base is. Okay. So now in context of BDS, or in context of programming, or in context of general computers and everything, we use these three these three bases. Base 10 is our regular base. We all humans use base 10, but computers can only work with base 2, and base 8 and base 16 is used because we cannot see a very long string of binary and comprehend it. Therefore, to make the representation compact, we use base 8 and base 16. If you see the actual machine code that gets generated, it will show you in hexadecimal. And the reason is because we cannot comprehend 64-bit or 32-bit binaries. We cannot comprehend them. It's not humanly possible. So we use these bases, which are big bases, which make them compact. Okay. So this is the reason why we use 8 and 16. Now we'll come to the main point because quiz is coming. So basically what is in this week is basically conversions. How you convert to base value, base 2 to base 10 and base 16 to base 8 and so on. Okay. So we'll start by, okay, tell me, do you understand all these conversions? I will only take those which you do not understand. Guys, tell me which basis you do not understand.
Just
हाँ
जो इम्पोर्टेंट वाले हैं वो भी बता दो भैया.
जो क्या है?
इम्पोर्टेंट इम्पोर्टेंट.
अरे important, all are important in one sense, but I will tell which one is are difficult. Okay, mostly doing these from 8 to 16, these kinds are difficult, but okay, I'll tell all of them. So basically, if you have a binary number, we will convert everything to decimal first. Okay, if you have base 2, you know the method. You have to use this thing that I have done here. Okay, basically from right hand, you will start with 2 raised to the power of 0 and just increase the exponent 2 square to cube, multiply these two numbers and add it, and you will get the decimal. Okay, the same is true for base 2 to 10, base 8 and 16. Same is true for them. If it is base 8, we have to just do the same thing 1010. If it is in base 8, just write this thing 8 square 8 cube, multiply these two and add it, you will get the decimal. Okay, so converting anything to decimal is pretty simple. You just have to write the base with correct exponent, multiply with the digit or the symbol and add it, you will get decimal value. The reverse is little bit tedious. Okay, for example, uh, if you have suppose 27 in base 10 and you have to do it, you have to convert it in base 2. Can somebody tell me the method that we use to convert 27 into uh, base 2?
Dividing by 2 and taking the remainder.
Yes, sir.
Yes, dividing by 2 and taking the remainder in
From
opposite way,
yes, sir.
opposite direction kind of. So here it is 27 divided by 2, it will be
One and
with
three.
remainder 1.
One. Then with
Again by
six.
2, it's 6 with remainder 1.
And then zero remainder.
It's 3 with 0 remainder
Then one.
and then 1 with remainder 1. And if you divide it, it will be
Zero.
0 with remainder 1.
One.
So this in uh, this direction.
Yes, sir.
X in binary is 11011. Okay, you can make sense of it in this way. See, what is the closest exponent of 2 to 27? It is 16, right? 16 is the closest, like which is lesser than 27. 32 is greater than it. So we cannot use that. Okay. So then if we add 8 in it, what will be it? 24. And we now have to add 3, which is 2 plus 1. If you see here, this is 16, this is 8, this is 2, and this is 1. So this will happen in this way. So if you know this method, you also know the opposite things for base 8 and base 16. You have to do just exact same thing with in case of base 8 you have to divide with 8. In case of base 16 you have to divide with 16 and take the remainder. And in case of base 16 you have to just change the 10 from 10 to 15 numbers to a b c d e f. Okay, so that is also easy, right? Any doubt in the conversions, basic conversions?
Sir,
Hmm.
I have a one general doubt.
Okay.
Uh, we generally use base 2, base 10, base 8, and 16. But
Hmm.
why we cannot use general values like 3, 5, 7, 10?
Base
Like,
3, base 5, right?
yes, sir.
So because see, we use base 10 because this is the way human brain like we work. So that is, there is no particular reason to the base 10. That is just what we use. Okay.
Okay,
We
sir.
use base 2 because we can represent just two values, 0 or 1 uh, in our computers, right? Therefore, this is the reason of base 2. That is understandable for everybody. Why base 8 and base 16? As I have told you, base 8 and base 16 is used to represent very long binary numbers in compact way. Like in base 16, this 27 can be represented in much compact way, maybe by 1. And what will be the remainder? 8 plus 2, 10, 11. So it will be 1b. Okay, here it took just two places, and in binary, it took C 1 to 5 places. So this is more in this small scale. We think that binary is better, and hexadecimal is kind of daunting to our mind. But if you think about 64-bit numbers, our computers work on 32-bit or 64-bit numbers, right? If you go and see those numbers, you won't be able to comprehend what is there in those 64 or 32 bits. So therefore, we use this base 8 or base 16, mostly base 16 in this case, to make the representation compact. Base 16 is better because see, what we can do, we can just take these uh, four digits and convert it directly to base 16, a single digit of base 16. Okay, and also is also true with base 8. We can just take these three digits and convert to something that is base 8 directly. We group the bits in 3 3 or 4 4 and convert them directly to base 8 and base 16. Therefore, we use these two bases. Just notice this is just 2 cube and this is just 2 raised to the 4. This is the reason we use base 8 and base 16 extensively and no base 3 or base 5. You got the answer?
Yes, sir.
Okay. So any other doubt?
No, sir.
Okay. Uh, so if you have to convert binary to 16, base 16 or base 8, I just told you how to you can do, like take a big number 1 1 0 1. You can just group them 4 by 4 and convert each group of 4 bits into just one single hex value. And if you want base 8, you can group it with 3 3, just add a 0 here and convert it to something in base 8 directly. See, what is the value of here? It is 3. So it will be 3. It is 2. And what is this? Uh, this is 4 to 6. So it will be in base 8, it will be 3 to 6 in base 8. And see, what is this? This is 6. And what is this? This is 13. So this is D. So it is D6 in 16. So this is also very simple. The only, I guess, harder, like computationally harder, is if you have to do it in from base 16 to base 18, right? In this case, what you can do, you can convert it to binary and then convert it to other base. that will be simpler, I guess, because changing the base inside the equation will be little harder. So what I'll recommend is just convert those numbers in binary. That is very simple. The similar way that we have done here, you can do the reverse conversion as well. Just take one digit, one uh, symbol, and convert it to the binary, and then convert that whole binary into other ways. So this part is also simple, but just computationally harder. You can make mistakes here. And also remember, try to reduce your mistakes and double check, because the exam is going to be objective, right?
Yes, sir.
So any error can cause you the entire marks of that question. So always reconsider your answer. That is very important.
Sir, can we direct convert octal to hexadecimal?
Okay.
Can we direct convert to octal to hexadecimal?
Yes. Right now I have forgot how, but yes, you can.
Okay.
Like the way we can convert from base 2 to any or decimal to any base, we can obviously convert the number to any base to any base.
Okay, sir.
So should we go ahead, or do you have any doubt in this simple conversions?
We
Do
can
you
go
get?
ahead, sir.
Okay, sir. And you can call me by a name, okay? You do not need to say sir. So
Sure,
now
sure, sure.
we'll see this one's complement, two's complement, and signed magnitude. We'll see signed magnitude first. Okay, so now we can represent any positive number and zero in binary, right? But to do algebra on computers, we have to also represent negative values also. So to do that, we actually not we, but mathematicians came with many methods. One of them is this sign magnitude method. To represent negative numbers using binary. Using binary, they came with many like sign magnitude, magnitude one's complement, two's complement. These three that I know of. If there is any more, I don't know, but there might be. Okay. So let's see what humanly possible is that we can just say this number is negative, right? We can say this, but how can we say the same thing inside a computer? Because computer cannot do this basic human thing. So therefore, first we are doing signed magnitude. So can somebody tell me what is signed magnitude? That is very simple, right? You go ahead and tell me how can I represent 5 minus 5 in signed magnitude.
Sir,
How can
like just adding a one in the binary, like usually it is, I think, 0101.
uh,
So we have to change it like in the MSB, we have to change it to one for the
this
negative
MSB,
five. So sorry?
this MSB
Yeah,
here.
sir.
Hmm. But you forgot to ask me that how many bits of signed magnitude the number should be.
Yes, sir.
so that you keep in mind. If anybody say two's complement, the one's complement or sign magnitude, you always have to ask how many bits you want. Because see, this that you said 1101 can be -5 in bit 4,
Yes,
and
sir.
10101 can also be -5 in bit 5.
Yep.
So bit, how many bits we are using is very important.
Yep.
Same is true for one's complement and two's complement. Okay. So basically what is happening here, this part, this part is exactly same as we do in unsigned binary, just plain binary conversion. We are just adding another bit as at the MSB to represent positive and negatives. So the first bit, if it is 0, the number is positive. If it is 1, the number is negative. So this is just basically a convention. Okay. If the first bit is 0, it's positive. If it's 1, then it's negative. Uh, let's see. Also, let's cover the sign extension part also in this section itself. So let's, if I give you bit 5, -5, and I ask you to convert it to bit 8, how will you do it? Can anybody tell me? If I give you bit 5, my -5 in signed magnitude, and I ask you to give me bit 8 signed magnitude of -5, how will you extend the sign? How will you extend the number?
Sir, we put 101 and before it uh, we put uh, 40 and 1.
40 and 1.
Yeah.
Correct. So basically, we will keep the unsigned part as it is, and will fill the gap between the MSB, which should be the 8th bit, and these three. So we will give 4 zeros. This will be 8 bit.
Yes.
MSB should remain 1, and we will just add zeros in between. This is the sign extension of signed magnitude, a representation of binary. Correct? Any doubt in this?
No, sir.
No.
No, sir.
No doubt. Okay. So you understood signed magnitude. It's pretty simple. Let's go to 2's complement first. Okay. Uh, see, what we do in 1's complement and 2's complement. If I ask you to convert, say here 1's complement, if I give you like this 1010, and I ask 1's complement of this number, what you will do is
Sir,
basically
we will invert it.
you will flip the bits, and you will say 0101 is the 1's complement of this number, right?
Yes, sir.
And if I ask 2's complement, you will add 1 in this, and that will be 2's complement, which is 0110, right? This is 2's complement of the same number. But do anybody understand what we are doing here mathematically, and why these numbers are representing negative numbers? Like, it's not straightforward like sign magnitude, that the MSB is 0, therefore it is positive, or MSB is 1, therefore it is negative. It's not like that. Does anybody know what this 1's complement or 2's complement is?
No, no.
See, I really want to tell you now, but the professor haven't mentioned anything about it. So after quiz, you can go ahead and read in Maris Manu if you have the book. It is mentioned there. Okay, the real meaning of 1's complement and 2's complement, and why they are used to represent negative numbers, and how we can do algebra with binary and do these things. do the subtraction using 2's complement and 1's complement. So right now I'll put that aside. So let's go and see how the conversion work. As you have told me, if you have to do one's complement, you will just flip the bit, and if you have to do the 2's complement, you will flip the bit and add 1 to it, right? Any doubt in it?
No.
No doubt. It's very simple. So
Yeah.
let's see how these one's complement and two's complement represent negative numbers. Okay, so I guess it is in week 3 or week 4. I do not remember, but it is there. So see, consider this number line. This is number line. This is our 0. We can use binary numbers to represent any number that is 0 or positive, right? But the problem comes with the negative numbers. Let's say we are doing let's say we are doing 4 bit we are using 4 bits. So what is happening? So we can represent, if we are using just unsigned numbers, we can represent from 0 to 2 raised to the power of 4 minus 1, which will come somewhere here. Okay, this thing in unsigned numbers. Okay, but obviously what will happen, we want to represent negative numbers also. So if we give some space of this band to negative numbers, obviously we cannot, then we will not be able to represent some positive numbers also. We are just moving this band sideways to in this direction. So what happens in one two's complement specifically, that is more important. I'm not talking about one's complement here right now, but what is happening in two's complement, that until 2 raised to 3, somewhere in middle, 2 cube, this portion, and we are using to represent positive numbers, which will be of this say until this number, from 0 to this number, we are using these no, we are using it to represent positive number, and from 2 cube, which will be 1000, from this number onwards in this direction until the last number, we are using this portion to represent negative numbers. What is important to understand here, that what happens, suppose this is minus 2 cube. Okay, from 0 we are representing minus 2 cube, these numbers here. So when, assume it is that we are just taking this block and putting it here. So what will happen, this minus 1 will go at the very end. So in 2's complement, you know that the uh, 1111 in 4 bit will represent negative 1 and not negative 2 raised to 3, and 1000 will represent negative 2 raised to 3. So we are going from 0 to 2 raised to 3 minus 1, and then just next number after this, which is this number, after this, just the next number will be minus 2 raised to 3, and from there we will again ascend, because these are negative numbers, it will go up. So what is the I guess this question exists in GA or PA somewhere, that what is the most smallest number you can represent in 4 bit 2's complement or 1's complement? This is a very common question that people ask, because you have to understand that we just take this block and we put it here. So the first number is actually minus 2 of 3, and it goes ahead until minus 1. And in case of 1's complement, it goes till 0. So in 1's complement, for in 1's complement, 0 has two representations. One is 0000 in 4-bit, and another is 1111, because one's complement of this is just 0000. Correct. So 0 has two representation in one's complement, but in two's complement it is not like that. In two's complement, positive numbers goes from 0 to in n bit two's complement. Uh, it goes from 0 to 2 raised to n minus 1 minus 1, and in negative it goes from minus 1 to 2 raised to n minus 1. These are the ranges of numbers that we can represent in 2's complement and 1's complement. This is in 2's complement, and in 1's complement it is from 0 to 2 raised to n minus 1 minus 1. The same thing that is here, just flipped in sign. So any doubt in range, because range is very important. Most people make mistake in range. Guys, any doubt in range? Am I audible?
Yes, sir.
Yes.
Yeah,
So
yeah, no doubt.
no doubt. I guess then this is just week 2, right? 2's complement, 1's complement, sign magnitude, and range. Any doubt in week 2 in general? You can go ahead and you can ask. Week 1, any doubt, or week 2 also? Any doubt?
No, sir.
No, sir.
No doubt. So basically, take in mind this: in week 1 there is just VTC and this equation, because we want to also consider some practical aspects. So VTC, the graph of VTC, small signal analysis, which is this equation, and noise margins. Noise margin is little confusing, but just like uh, if you think, if you give some time to it, you can do correctly. Okay. And in week 2, there are those all basic conversions from base 2 to 816 all and 10, and 1's complement, 2's complement, sign magnitude, and ranges of all those numbers. Am I missing any topic? All topics covered in week 1 and week 2, right?
Sir,
Huh?
sir, can you explain me about fraction from week two?
Fraction.
Yeah.
Yes, we forgot about the fraction. So see, it's just the extension. Do anybody want to explain him how fractions work in any other base? Because you understand how it works in integer. And does anybody want to explain?
Yeah, sir. It's
See,
okay.
see, see this
Sir,
equation. What do you think? How fractions work?
Sir, it would be, I think, will be in minus power, like negative power, I guess.
Correct. It is just place value system, and the uh, first digit after the point has 2 raised to 0, and it's going up. So and the value of the place before it will be 2 raised to minus 1, before that minus 2, and so on. Okay. When it comes to conversion, like we have this division method here. Similarly, we have multiplication method when it comes to the fractions. So for example, if it is like 0.75 decimal, we want to convert it in binary. How we will do? We'll multiply this fraction with 2. Okay, what is double of 0.75? 1 plus
1.5.
0. 1.5, sorry. So what we'll do, we'll take the 0.5 and we'll write just the 1, like this is point 0.1, 1 from this, um, the digit that went ahead the fraction point. We'll take it, we'll write it here, 1. What is double of 0.5? 1. Okay, and 1.00, so 1 will come again here, and it will become just 0.0. So 0.11 in binary is 0.75 in 10. If you convert it from binary to decimal again, this is 1 by 2 and this is 1 by 4. So it is 0.5, this is 0.25. Addition of this is again 0.7. The same thing is true for base 8 and base 16 also. Multiply this. Huh? Go on. Hello? Somebody called me.
No, it is
Okay. In base, if you want to convert it into base 8, multiply it 8, whatever comes before this point, after the multiplication, write the symbol in that base for that. In case of 8, it will be just whatever value comes here. In case of 16, you have to do the ABCD thing. Take the remaining fraction, multiply it with the base again, and do it until you are satisfied. Because what happens here, because it is fraction, you may or may not be able to represent it in enough bits. Here it stopped after 2 bits, but it may not stop ever. Okay, so it will be mentioned, specified in the question, how many bits after this point, fraction point, they want us to write the number. So do it till that digit, and that's the fraction. But on a tangent, if you want to see how this thing works in computer, because computer do not have this point, right? Computer can only understand 0 or 1, no point computer can understand. So how it happens in practical way is by fixed point representation and floating point representation. If you have any curiosity, you can go and search for it. Fixed point, I guess you have learned about in programming in C, right, guys?
Yes, sir.
Fixed point representation and floating point. You, if you have curiosity, you can go and check how this thing is implemented in digital systems. So okay, I guess now we have covered all the topics of week 1 and 2. Any doubt?
No.
No, sir.
No doubt. So should we go ahead with week 3? What is the time? 10:20. Okay. So I guess we have covered the sign extension for signed magnitude. Okay, we have not covered it for ones and twos complement. Okay, we'll cover that first. See, now tell me what is the ones complement representation of -10 in 4 bits? In 4 bits. What is 4-bit ones complement of -10?
1110.
1110, is it?
Sir, 11010.
Can we
Sir, 1010.
1 0 1 0. 1 0 1 0 will be unsigned, right?
Yeah, sir.
Yes, sir.
So it's mistake from my side, but also mistake from your side. Can we represent 10 in 4 bit if it is negative in 4 bit one's
Mm,
complement?
No, sir.
Can we represent? What is the
mm,
maximum number that we can represent in one's complement with 4
5,
bit?
sir.
5.
Maybe. Yes, sir.
Uh, because see what will happen?
sir, I
There are
think 7. 7.
yes, 7 is the maximum number that we can represent with 4 bit because this bit will has some different weight here.
Yeah.
We can represent maximum minus 1. So let's do it 5 bit. In 5 bit, we can represent till 15. So tell me, what is the 5 bit representation?
11 0 1 0.
Sir, it would be 0 1 0 1 0.
How it can be 0 1 0 1 0?
Oh, sorry. Yeah.
It will be 1 0 1 0 1, right? See, this is
Oh, yeah.
what
It's
is
one's complement. Yeah. Sorry, sir. Yeah.
uh, so this is negative 10 in 5 bit, right? So what if I want to do it in 8 bit? Now tell me what is minus 10 in one's complement 8 bit? Calculate it and tell me when you are done.
Sir, 1 1 1 1 0 1 0 1.
What?
1 1 मस इसके आगे मतलब 1 ही लगता जाएगा 8 जब तक 8 बिट नहीं हो जाएंगी तब तक 1 के आगे
1 1, how many ones?
सर 4 4 1
4 ones. Then
0 1 0 1
0 1 0 1. How many digits is it? 4 and
8
4, 8. Okay.
yes sir.
So have you seen this? It was 5 bit. This is 8 bit. What happened? How did we extend it? Sorry. How did we extend it? The sign. Here is the number that we converted to one's complement. Here is the MSB that won't change because this is how it works. What did we do? We just added ones that was required. Number of ones that was required in between the ones complement and the MSB in between them. Okay, we just added ones. Can somebody tell me why one or why not zero? Because what we generally do, if we want to do 1 0 1 0, we want to do it in 8 bits, we'll just add 4 zeros in front of it, like right in normal unsigned binary, we will just add zeros. Why are we adding one here? Any idea?
बट टूज कॉम्प्लीमेंट में दिखाते हैं ना नेगेटिव नंबर, वंस कॉम्प्लीमेंट में नेगेटिव नंबर कैसे दिखेंगे?
We can represent negative numbers in both ways, in one's complement also and in two's complement also.
So is that using sign magnitude or
Huh?
representing negative numbers? Is it using sign magnitude or something else?
It is in one's complement. Right now, we are doing in one's complement.
Got it. Got it.
So we can use all three: sign magnitude, one's complement, and two's complement to represent negative numbers. It's like one's complement and two's complement are strongly related, just little bit of differences there, and sign magnitude is like entirely different. So see what is happening. Just I told you here above what we are doing here. We are taking this whole block and putting it here in one's complement and also in two's complement. So where is minus 10? Minus 10 will be somewhere here, right? Because it's in it's here. S- Uh, this is minus 2 raised of minus 3, but forget about this. Let's consider 2 raised of 8. So it will be somewhere in this side. If we take this block and we are putting it here, will it be this side or will it be this side? Obviously, this will be this side. Okay. Basically, what we are doing, minus 1, minus 2, minus 3, we are going in opposite direction. Uh, we are taking 1, 1, 1, 1. Uh, we are taking 1, 1, 1, 1 in, let's say, 5 bit, 1, 1, 1, 1, 1, assigning it to 0 in case of one's complement, and then we are going below. So 1, 1, 1, 1, 0 is minus 1, and so on till we hit 1, 0, 0, 0, 0. This is basically what we are doing in one's complement. In two's complement, this thing won't be 0. This will be minus 1. This is one's complement. Uh, in two's complement, what will happen? This will be minus 1. This will be minus 2 until this point, whatever corresponding number is here. Okay. So this is happening. Therefore, we append ones here rather than zeros because we are uh, going in this direction. And if you ask me mathematically why we are doing it, so also think about it this way. If I ask the same thing in unsigned magnitude, you will do this, right? And if you take one's complement of this number, what will happen? It will be 1, 1, 1, 1, 0, 1, 0, 1. So all these zeros will become ones in one's complement and two's complement.
Right,
Therefore,
so
ones
because
and
it pad the bits for zeros.
huh?
So because it pad the bits to match the bit width.
Huh, we are using zeros here, but we are using ones here because this is a negative number. If I do the same thing with 10, let's say 10 in 8 bit, I will not do 1. I will just say 0, 0, 0, 0, 0, 0, 0, 1, 0, 1, 0. I will not sign extend it with 1. I will extend it with 0 because it is positive and it will behave same as unsigned numbers behaves. So basically, rule of thumb is whatever the MSB is, just copy it as many number of time as needed. If it is 0, pad it with zeros. If it is 1, pad it with 1. This is how sign extension work in one's complement and in two's complement. There is underlining mathematics here. Okay, if you want to, you can go and read Marisman after quiz 1. You will like it will if you are interested in it. It will be fun and joyous to see how these things underlying mechanism in math work. So did I confused you more or did I made it simple or did I explain it?
Sir, I'll be honest, it is a little bit of both, but it was definitely interesting.
Yes, yes. Because if you go little deeper, it will be little confusing and harder, but it's fun. But rule of thumb for quiz 1 is if it is 1, extend it with 1. If it is 0, extend it with 0 in case of one's complement and two's complement. Otherwise, extend it with zeros in case of signed magnitude and unsigned binary. That is it. Okay. So what else is in week 3? You do not have any doubt, right? Or if you have any, you can ask. Any doubt?
No, sir.
So you get the signed extension.
Yes,
Uh,
sir. So I have a quick doubt. In week one, did
okay,
you
okay.
explain this one equation method? I
Yes.
joined a little late. I was a bit tied up.
Here it is.
Yes, sir.
So basically, what you have to do is take the derivative of the equation with respect to vi. Wherever the derivative, which is also the gain of the gate, is negative, those
Which was
points
inverter,
are
right? Got it.
point of interest.
Got it, sir. So when you
So,
equate that, we'll get the answer eventually, right?
huh,
Actually, I was fumbling with that before this joining this.
huh. So let's go to the gates now. I guess it's there are gates in week 3. So all of us have studied basic gates in 12th. Yes,
Yeah, yeah.
we have studied basic gates, so we all know what is a NOT gate. Uh, uh, First of all, NOT gate. Explain me NOT gate. Any one of you explain NOT gate.
So NOT gate is just like that inverter that sir showed to us in the lectures. It just invert the in whatever we give the inputs are like if we give zero, it will make it to one. If we give it one, it will make it zero.
Correct. So let's draw the truth table for it. So if x is 0, the output will be 1, and if the input is 1, output will be 0. It's very simple, basic get, NOT get. How is it represented in Boolean algebra?
X is equals to y bar.
X, no, y is the output, right?
Yeah, yeah. Oh, so y is equals to x bar. Sorry.
Actually, your statement is also correct, but here, output is y.
Yeah.
So basically, this is the Boolean expression for this basic NOT gate. So let's go to the next gate, which is AND gate. Somebody explain now what AND gate is.
If both of the inputs are one, then it returns one. Otherwise, it returns zero.
Correct. So if it's A and B are the input and Y is the output, 0, 0, 0, 1,
1 0
1, 0.
1.
So tell me the output.
So 0 0 it will return zero.
Hmm?
In 0 1 it will also return zero,
Hmm?
and 1 0 of course zero, and 1 1 it will return one.
Yes. So somebody said if what 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 did you tell me? What was the AND gate? Somebody told me, right, while I was drawing this symbol.
Yes, sir, that was me. If they
So
both
what
are
did,
one, then it returns one. Otherwise, it returns zero.
yes, but what if there are n inputs?
If any one is zero, it will return zero. Otherwise,
Correct.
all need to be one to return one.
So
Correct. So
basically do multiplications of the input.
we use multiplication sign in Boolean algebra to represent AND gate. So y is equals to a dot b here. The output of this gate will be high only if all the inputs are high. If any one input is low, the output will be low. This is basic AND gate. And this is the Boolean expression for AND gate. Okay. So now let's do the next gate, which is OR gate.
Yes, sir.
What is OR gate?
So it do summation of the two inputs or n inputs that we provide to the gate actually.
Summation. But what will be a better definition? The way I did it for AND gate.
Sir, if we put all inputs in 1, then its output will be 1, otherwise 0.
If any input of this gate is high, the output will be high. It does not care if how many zeros are there. If any one input is high, the output will be high. So tell me the outputs here.
Yes, sir. So 0 0 will be 0,
Hmm?
0 1 will be 1, 1 0 will be also 1, and 1 1 will be 1.
Hmm. Uh, so which gate is next? NAND gate. Let's
And get
we didn't write the equation. It's y is
yes,
equal to
A plus B.
A plus B. Here, the meaning of plus is not addition, okay? Because if there are three inputs, 1 plus 1 plus 1, it should be 1 only.
Yes, sir.
So don't add. So NAND gate. So tell me, what is a NAND gate?
Combination of AND gate and NOT gate.
Combination of AND gate and NOT gate.
It's, a, it's an AND
So
gate
what
with a
will
complemented output.
so what will be the definition the way we did for rest of the gates?
So like if both the inputs are high, it will return 0. Otherwise,
Hmm.
it will return 1.
Hmm. So what we can say, if any input of NAND gate is low, the output will be high. Correct.
Yes, sir.
Uh, so what is the y? What is the value of y here?
So sir, it will be for 0 0, it will be 1.
Hmm?
0 1 also 1. 1 0 will also return 1, and 1 1 will return 0.
0. And what is the Boolean expression?
It will be y equals to a dot b, and on that it will be a bar. There will be a bar actually.
Uh, a dot b complement, right? A dot
Yes,
b
sir.
bar.
Yes, sir.
And in similar fashion, what is NOR gate here?
It is a combination of NOT gate and OR gate.
Yes, it's combination of NOT gate and uh,
OR gate.
so NOR. It's the symbol is basically so tell me the definition of NOR gate.
Same thing as NOR, OR, but it's inverted. So 0 0 will be 1. No, wait. Yeah, 0 will be 1, right? Or 0 1 will be 0, 1 0 will be 0, and 1 1 will be 0.
So basically, if any input is high, the output will be low.
Yes,
Correct.
sir.
So now which gates are remaining? XOR and XNOR, right?
Yes, sir.
So let's do it for XOR. Sorry, we didn't write the
Yeah.
Boolean.
Boolean expression.
So it will be y is equal to
A plus B complement.
a plus b complement. So now XOR. Tell me the definition of XOR.
If the input values are complement of each other, then the output is high.
Hmm. And what if there are three inputs?
So if all inputs are equal, then it will be 0. I mean to say low.
What? Repeat again.
If all inputs are equal, I mean to say if inputs is 0 0,
Huh?
then output will be 0, and if inputs 1 1, then also is 0.
What will happen in case of three inputs, like 1 1 1 or 0 0 1 in those cases?
So in case of a two input XOR gate, we can say that when the inputs are different, the output is high. But if you want a general definition, then we can say that if the number of one inputs or high
Mhm.
inputs is odd, then the uh, output will be high in
Yes,
case of
that
any.
is like more general definition of the. It is basically odd parity checker.
Right.
If there are odd numbers of one in the input, it will be high. So here it will be 0 1 1 again 0 because it's even here. Same is true for any numbers of input of XOR. Okay.
Sir, there is a I don't know, like there's a confusion between when we talk about function and three input OR gate, a gate and a function
Mhm.
definition. I think there was a post on the discourse forum also about this.
Yes, yes.
Yes,
Did you made that post?
yes, sir. The
The
confusion is
it's
still there, but anyways,
please guys, discourse. Please use discourse because it's much better way of interacting because we can do a lot of things on discourse. We can post photos, videos, latex is there, so we can use all those resources and we can connect with instructors and everybody else directly. So because right now discourse is like very empty, there will be just one or two posts in a week if any.
After quiz 1, please teach us how to use the discourse.
Yes, we are discussing about that. A lot of people do not know how to use discourse.
Yeah,
uh,
please
they
make
are
that session. It will be
uh,
very helpful to everyone.
yeah, it can
yes,
serve as
yes.
a knowledge base for the students.
And
Can correct
also
as well as future.
all the questions that previous students have asked are also there. So
Yes,
it's like a database of knowledge. So please consider using discourse.
but sir, the sometimes the the response time is very high.
Yes,
Some,
we are
for some
working
of the
on
other
that.
subjects also, I've
it's
experienced that.
it's like for most of the very few people have managed to reduce the response times and we are working on it. Okay, so
Okay, sir.
we'll fix those things. You start using it.
Okay, sir.
Okay, so the controversy about XOR and XNOR. So basically, what uh, the thing is, definition wise, what XNOR should be is complement of XOR, right? It's
Yes, sir.
XNOR, so it should be just complement of
Yes, sir.
XOR. But In practice, the XNOR gate is not much used and it's not properly defined as well. So therefore, in one of the week's GA, I guess there was this question where Ankit sir said that XNOR output of three input XNOR and output of three input XOR will be equal, right?
Yes, sir.
That does not make kind of sense because by definition they should be opposite.
Yes, and I wasn't able to find any ICs also for three input XNOR gates. Most of them are only three input XOR gates, and they use the complement of that
Yes,
for
yes.
implementing XNOR.
So basically, what happens is what exists in practically is this A XOR B XOR C whole complement. Okay. And what was asked in that question was A XOR XNOR B XNOR C. If you implement this one with logic gates, it will be like uh, two XOR gates. Okay, two XOR gates, one after other. And then NOT gate. This is what XNOR that exists in practice. This will become three input XOR and we are just doing a NOT operation on it. This is XNOR in one sense. Also, what this is uh, doing XNOR in cascaded fashion. So these are clearly two different things. Okay, this was what was asked, and this what you thought was asked.
Yes, sir.
And it's not your fault. Okay, all
Say
batch
it's a
that came before
function,
you did the same
then fine.
mistakes.
Yes.
Huh?
If they
What?
say it's a function, then okay, we can assume it's A XOR B XOR C. But if they say it's not mentioned over there.
Even if they mention it's a function, what are you meaning by function? Are you meaning this or are you meaning this? Because these two things are complements of each other. If you draw truth table, it will be exactly opposite of
Right,
yes, you have seen that.
right.
So basic like learning from that question is XNOR gate is not clearly defined, so it does not matter kind of. In practice, it does not matter because it is not clearly defined.
Right.
Uh, so if there will be any question in quiz about XNOR, then we can ask to sir to like I don't think they will put XNOR questions in quiz because they are not clearly defined and that very easily we can make mistake in this. Okay,
Can
This
we
so
is
skip
I
this?
have a quick
not
question.
huh?
Sir, I have a quick
What?
question about this one. So
Okay.
regarding these XOR, XNOR, and this one gates, I remember seeing multiple questions where we were asked to find the least number of circuits we could do this. I'm not sure it's already discussed,
Hmm.
but what is
Hmm.
the fastest way to approach the problem, sir? Because doing it the hidden trial method takes way too long.
Yes, doing it with hit and trial, it will take way too long. One thing you notice that if the expression, whatever the Boolean expression is, if it's a long expression, obviously it will take more gates. If it's a short expression, it will take less gates. Okay, like if it has like five terms and one equation has just two terms, small terms, obviously the smaller one will take less gates. So simplifying the equation enough is one thing. And see, this is a question that even in practical way there is no like straightforward algorithmic way to solve it. So you have to think about it. Like right now, I do not know any way by which you can do the least gates with like a methodical way.
Got it, sir. So we optimize and just pray for the best.
Yes, and in case of questions, it won't be like very big systems. It will be very few gates to start with, and they will ask to reduce them. So you will have enough time to think about it.
Okay, so the minimum number of gates questions usually don't come, right? Because I saw that as a pattern in the previous year papers also. They such questions do not come.
I haven't analyzed the PYQ, so I have no idea
No
about
worries,
it.
sir. Yeah. No, we won't take your word as final, of course, because you never know what
Obviously.
happens. But we still appreciate your input.
Uh, so let's go ahead. I'm not drawing the truth table, okay, because it is like controversial. So what is the next topic here? We have done basic gates and truth tables, logic circuits. So see, now we have came to the point that in this case, we have to do questions. Okay, if we want to excel in logic gates, we have to like go see the circuit, build our own circuits, and analyze the existing circuits in the questions. So that's a practice thing in case of gates, because gates themselves are very simple. I can tell you what kind of question can come on the gates. Like they will give you some circuit and they will ask what should be the input so that the output is one particular value, 1 or 0, and those kinds of things. Or they will give a circuit and will say replace all AND gates with NAND gates, and then what should be the input so that the output is some particular value. Or they will ask to reduce, as somebody asked, that reduce the number of gates. All these kinds of question will come in logic circuits. Okay. Uh, and then there is this Boolean expressions. Okay. Boolean algebra. You really have to practice Boolean algebra also, because there are some patterns that you get only by practice. Nobody will tell these patterns exist. Okay. Like you can do step by step manner and come to some conclusion, but if you do enough practice, you can like reduce some step. You can see some patterns and you can directly write a smaller equation for those patterns. Okay. So for example, if there is some b plus bc, you can go ahead and write it as b plus b into b plus c, and then do it that this will be just 1 itself, so it will be just b plus c. If you know this thing, you will directly write it as b plus c. Okay, because the exam is not subjective, so there is no marks for the steps. If you can reduce the steps, you will reduce the time you will need to do the questions. So practice is very, very important in case of Boolean simplification and also the gate questions or the circuit questions. So please consider doing enough practice. So the next week is week 4. What is the timing right now? It's almost 11. So I will just explain what I won't explain properties of Boolean functions right now, because these are like basic things, associative, distributive. I will explain De Morgan's law, and then I will explain the sum of products and product of some canonical representation. Okay. Are you fine with this,
Yes,
guys?
sir. Yes, sir.
Yes, sir. Yeah, yeah.
Okay. So it's almost time. So basically, what is De Morgan's law? We have studied De Morgan's law in set theory and also in 11th class in Boolean algebra. Basically, if we want to take complement of A plus B complement is basically A complement into B complement. Okay, so complement of individual terms but not in or operation and operation. And A dot B bar will be A bar plus B bar. If you remember the basics of set theories and all, you can understand why it is the way it is. Because what you are saying in A plus B, A or B, any one input will be high, then the output will be high, and the negation of it will be if any one input is low. Sorry, when both of the inputs are low, the output should be high. So you uh, have to use AND operation because it says when both of the operations are high, the output will be high. And because we want to do uh, 0 in case of one, we want to see if when both inputs are low, the output should be high, then we are doing complements of individual terms. I won't complicate this thing for you because I think I'm complicating it. Basically, remember this thing: A plus B is equal to A bar dot B bar. A dot B bar is A bar plus B bar. Okay, this is De Morgan's law. Is it just Morgan? Or is it De Morgan? I didn't remember it. Okay, so De Morgan's law.
Sir, it is DE space
Hmm.
Morgan's apostrophe S law.
Hmm. So okay, now it's fine. De Morgan's law. So it's a very basic thing, but very powerful because if you miss this and if you write it as this, then you are gone. Yes, be aware of all these things, okay? Because in not hesitation, but because there will be just a time limit on our questions, we can do silly mistakes like these, okay? So be aware of these. Just one silly mistake will cost you the entire question. This is incorrect.
Yes, sir.
So,
Just a single bar also changes the answer.
uh, yes. So what there is now canonical representation. Okay, so you know the basics of Minturn, or what I will do, I will explain the basic why the that those things are the way they are. So consider a truth table. Okay, suppose there is some A, some B, and some C. Okay, and there is some output Y. Uh, that is some random, not random actually, but some output Y. Okay, this is a truth table. If we draw these truth table for all the circuits, it is not feasible. Therefore, we use Boolean expressions, right? Professor has mentioned it. If you use truth table for all the things, it won't be feasible because it goes the number of lines in the truth table increases exponentially. So therefore, we came up with Boolean algebra, but Boolean algebra is kind of complicated to represent because you cannot just look at at a equation and understand what is there. So therefore, people came up with this min term and max term representation of a truth table. So basically, we'll start with min term. Okay, min term, which is basically SOP, sum of products. Okay, sum of products. So in this, what we do, see in this truth table, if we can write a Boolean expression uh, for all these ones, okay, a expression that will be high only for these 5 specific cases and not any other case, then that equation will represent this truth table, right? If we can make an equation that will that will be high only for these 5 specific cases, otherwise zero, then that equation is the equation of this truth table. Now tell me, how can we ensure that the equation will be high only for these five cases and not any other case? Can somebody tell me, how can we ensure this? It's 11, so I won't ask you. So see
You
what
add
is
them up.
happening.
You add the ones. So if any one is high,
Hmm.
you will have a, high equation for that.
So let's go by how we will represent, how we'll create a um, expression for one specific case that will ensure that this case will always produce a high output. We can basically, what we do, we know when C is 1 and AB are 0, uh, the output should be 1. So basically when A is 0, so we'll take complement of A, and B is 0, the complement of B, and C is 1, so we won't take complement. This term will be high only in this one case, and it will never be high otherwise. Okay. If C is not 1, it will be 0. If A or B anything is 1, it will be 0. So we are ensuring here that it will be high only in this one specific case. We can do the same for all the remaining cases. Like here it will be A bar, B, C bar. We are using AND here because AND is what? AND will be high only when all these three are high. So those definitions are important. They come handy here. So we can do this for all. So it will be A, B bar, C here, A, B, C bar, and this is ABC. So now what is the way that we can say that if any one of these term will be high, then the output of the whole equation should be high. That is the exact definition of OR gate, correct? We said OR gate is something that's output is high if any one input is high. So what we do, we OR all these terms. So we will OR all these terms, and the equation generated from this equation is sum, because it is sum of products, because these are products, sum of products, SOP, also called as minterm. Minterm representation also works in this way. We can say this is 0, 1, 2, 3, 4, 5, 6, and 7th. So we can represent this equation by these numbers, m of 1, 2, 5, 6, and 7. Why we can use these numbers? Because this truth table, this part of ABC, for any three input, this part won't change. This will be always same. Only the output will change. So we can assign a number corresponding to every line, and we can just say take minterm of this line, and this will represent our system very compact manner. Okay. And now we'll see what you have any doubt in minterm. Did you
So,
get
sir,
what
No,
to
minterm?
summarize, let's say we take 0, 0, 1. We apply it to this. 1 will
Okay.
always be 1. So, 0
Hmm?
complement is taken A bar, B bar
Hmm?
complement is taken 0. That is
Hmm?
why it makes it 1, right? So, to
Yes,
match that,
yes,
we are using it like this, right?
yes,
Okay, finally clicked after a long time.
yes. So it is very simple. We want to create one equation, one compact way of representing this big truth table. Now we are just doing three. Imagine it for 32 bits. So doing even in like Boolean algebraic way, it's a lot of terms. Doing it in minterms and maxterms will be much simpler. Therefore, we come up with this. So see, what is happening now in max term? Can anybody explain me by using the same analogy what is happening in max term? which is product of sum.
So we are doing it for the zeros instead of
Huh.
ones. We do it for zeros,
What
and
do you mean we do it for zeros?
for the output is low, where the output
Hmm.
is zero. So when we take it, uh,
Hmm.
we add those terms A, B, C, and then
Hmm.
we use a product of those sums.
Okay. So basically, the way how we said it in it is for one, like if we can create any equation that will be high for only these specific five cases, it will represent this whole truth table. In similar fashion, if we can come up with a equation that will be low for only these three specific cases, that will represent this entire truth table. Correct. So how can we first of all create terms? So the output of that term should be zero whenever these three inputs are zero. So what we can do, we can say, so I'll copy it first. So this is max term.
Hello.
Okay. Huh?
Sorry for disturbance, but I
Huh?
want to know this content is from which week?
This is from week 4.
Okay, and this is for revision session for quiz one.
Yes.
Okay, because no, not uploaded on my Google Calendar. That's why now I am attending a C
It's recorded.
programming.
Okay,
Okay,
it's recorded. You can watch it later.
okay, thank you.
Okay. So we were at the terms. So how can we ensure that the output of this term will be always zero when all these for this one it should be zero. Okay. For in this case, we can just do A plus B plus C. Why not A dot B dot C in this case? Because even A dot B dot C will be zero. Guys, hello? Am I audible?
Yeah,
Yes.
you are audible.
Uh,
Yes, sir.
Yes, yes, sir.
So what we said here, why are we doing a product here? Because if any of this term becomes zero, this should become zero. Okay. Otherwise, this won't work. In similar fashion, what we want here, if any of this term becomes one, it should become one. This is the exact definition of OR gate. Therefore, we are using addition here, OR gate instead of dot. So see, if C becomes 1, this becomes 1 immediately. In similar fashion, here it is another 0. We want to create a term that will be 0 for this term only, which is A because A is 0 plus B bar because B is 1 and C bar because C is 1. This will be 0 only for this one term, otherwise it won't be. And there is this term, which is A bar plus B plus C. Okay. So we came up with these three terms. Those will be 0 for in these three cases. We want to ensure that if any one of this is 0, the whole equation should be 0, which is the exact definition of AND gate. And therefore, what we do, we multiply these three terms, and multiplication, this multiplication will create product of sum. because these are sums and we are doing product of it. Why are we doing sum? Because it should be 0 in this just one specific case. If any one of this flipped, this term will become 1. So it is 0 for this one specific term, and all these, if any of these term is 0, the whole output should be 0, and therefore we are doing here the product. So this is product of sum, also known as max term, which is represented.
So even while doing that, I saw that we were doing it on we were inverting the element on element to element basis. Why is that again? Could you explain once more?
Where?
So for example, there's A plus B plus C. In the previous SOP, we took A bar, B bar, C bar.
Okay.
I mean, if we were doing this, if it was 1 here, we would be doing A bar, B bar, C bar. But instead here we're doing A plus B plus C, even though it is a 0. So we're complementing that, right, on an element to element basis. So what's up with that? Like it makes sense when I think about it, but I want to understand on a more systematic level.
Okay. So what we are doing here, if you take, let's see, what will be minterm of this? It will be just A bar, B bar, C bar, right? What is complement of it? It is complement of this term is A.
Right, A bar plus B bar
A
plus
plus
C
B
bar.
plus C.
Okay. Oh, because double bar cancels out. Okay.
Yes, which is max term of C. Here it is the max term. So basically,
got it, sir.
if you want to make min term to max term or max term to min term, they will give you this expression m of something capital or small depending on min term max term.
Min term maximum, yeah.
Write those. See which numbers are not there. Okay. Take those min terms or max terms and just invert them. You will get SOP or POS in whatever you want.
Got it. So when we invert them by hand, like element to element basis, it is getting us there.
Yes.
Got it, sir.
The one which are not written in this representation. Okay. Not these 1, 2, 5, 7, 6, 7. If you invert them, you won't get the max term.
Okay.
You will get POS because this inversion of this will create a product of sum, but
yes,
that
sir.
won't be
Okay.
max term.
Got it.
So you have to do it for the ones that are not present in this min term.
Okay, so we're in this when we're inverting the value itself, we're inverting the set. So it'll be like 0, 3, like that. Got it, sir.
I didn't get.
No, like in set, when you're inverting it, you will get the other elements which are not in that set. I'm not able to explain this.
Yes.
Got it, sir.
So this is like a very simple way of doing SOP to POS, not SOP to PS, but min term to max term. So also this is a different between SOP and min term max term. Okay. SOP is basically just sum of product. Any sum of product is SOP. Any POS is POS. But min term is a specific SOP that represent this whole truth table in this manner, where we have all these terms. It will be min term. So you understand what min term and max term is, okay? And any doubt?
So that means for min terms and max terms, all the variables will be present in the form. So for if it's a product, then will have ABC. One of them will not be missing when we talk about that.
There might be, because what you can do, you can simplify this equation, right?
Okay. So but when we say talk about min term or max term, then all of those variables will be there.
If
right?
you get this representation, you have to write all the variables that are there.
Okay. So.
But if you get a function, like say a function of A, B, C, and some expression that might be a simplification of this entire expression because it can be simplified.
Okay, sir. So, okay, sir.
So,
So, when we are drawing the K map, the
huh,
first values which we put in, those are the min-term values, and then after simplification, that we get, that's the simplified form. That
yes,
may be okay.
when we put inside, we put this, and
Okay,
what we get is a simplified way, a
right,
simplified expression,
right.
a function.
Okay, sir.
And also, guys, K-map is in week 5, but you can use it in quiz. There is no restriction. So if you know and if you can apply, use it.
Yes, sir. For simplification, it will be easier. Yeah,
It will
papers.
K-map K-map makes expression so easy that I am confused how to make hard question on it. Okay, so it's very powerful tool. So I guess we have covered all the weeks. Anybody has any doubt?
Sir, could you quickly go over the base finding process once more? If you've already done it. I missed the
Base
first hour.
finding. Base
Yeah,
finding.
let's say this part, the example, let's say 16 base x is this value. How do we find
Hmm.
what x is?
Okay, so what you are saying is, suppose 16 base x is some value is given and value of this
Yes,
base is
sir.
known.
Yeah, yeah.
Base
Usually
is known
questions are
from
there like
B.
that, right?
Huh. So what you can go to the basics always. So what is this in decimal? It will be just 1
Right.
into x raised to 1 plus
Mm-hmm.
6 into x raised to 0. This is equal to this
Okay.
value m in base B. You can write the same value in B base the way I have written it. Okay. This will create an equation. So it is x plus 6 is equal to m. Let's suppose B is 10. Solve for this equation, you will get base. It's
Got
very
it, sir.
simple.
Thanks. I was doing it more of a hit and trial method, so this is good to see. I will practice
Yes,
this.
yeah, you do not need to do hit and trial. You can do it by equation way. There can be also questions like 16 in base x is some other number in base y. So what is the relation between x and y so that this equation is true? You can do the same thing using this method. This method is always valid. So any other doubt?
Sir, what is, sir, can you tell me Boolean expression of a max term, min term representation?
Uh, Pardon, can you repeat?
Sir, Boolean expression of max term and min term.
Boolean expression of max term and min term. Like you are given this thing, this min term expression. You want to create
Hmm.
Boolean expression from this.
Yes, sir.
Okay. Uh, so it will be mentioned how many variables are there. Okay. For because if you just see this one, you can think that there are 3 variables, but there can be also 4 variables. Okay.
Okay. Okay.
So the variables will be mentioned, and what you have to do, you have to remember these values. These values. Okay. These values are important. These are the values
Yes,
that
sir.
will be there in those brackets. These values correspond to the truth table. Okay. So if, for example, here it is 1. Okay. So what we will do min term of 1 in case of 3 variables will be, so what is 1? It is 0, 0, 1. Okay. It is 0, 0, 1. And let's assume A, B, C. Hmm? So
Hmm.
how can you make it 1? The output of that product should be 1. So we have to complement A because it is 0.
Hmm.
Complement B, it will become 1 again. And C can be as it is. This will be the value of this first one. Okay. Same way you can do it for 5, 2, 5, 6, 7, and just add them. In case of SOP, in case of min term, if it is max term, whatever the value there is inside this expression, it will be capital M or pi, okay, because it is product. So similarly, go to those write those numbers from truth table, and in case of max term, you have to create expression that will always result in 0. So in this case, if we want to do max term of 1, it will be A plus B plus C bar, because C is 1, we will complement it, which will create 0. And addition of all these 3 will be 0. This is the max term. This is the min term. Create all those expressions and just write a product of it. That will be the max term representation.
Okay, sir.
So any other doubt?
No, thank you, sir.
It's 11:22. So do you have any doubt, or otherwise we will end the session? It is.
Yes, sir. Thanks a lot for coming and helping us out like this. Where can we access the recordings?
It will be shared
I
soon. We will share the recording. I will share you the YouTube link. We will upload the recording there.
Oh,
Okay.
perfect. Thank you.
Thank you, sir. Thank you so
Thank you
much.
guys for joining, and
Thank you
thank you
so much.
Prathamesh for the amazing session.
Thank you, sir. Very thank you for your amazing time.
don't call me sir. I am just one of you.
Thank you, brother.
That is better.
Sir, I
Thank
look
you.
forward to having a discussion on discourse after the quiz.
Oh,
Yeah.
yes.
Please
Okay.
have it. Yeah.
भाई यार बहुत मदद हो गई यार, सही है।
हाँ
Yes.
नहीं पढ़ा था, समझ गया, पास तो हो ही जाएंगे।
उतना तो हो ही जाना भाई, मतलब।
All the best guys for your quizzes.
Thank you so much.
Sir, I'll put it this way.
लिनक्स
You've
और सी
gotten
का
us
भी
from
कराएंगे
passing
क्या?
one level to one level above, at least for sure.
See,
1 to levels above.
so for this term, means for quiz one, we have very short plan, but yeah, we are looking forward to take some another subjects for the electronics and quiz two.
Also, please conduct this session for electronics and electrical circuits for quiz 2.
Okay, we will
Linux
try
and C
to.
programming as well.
Okay, we will try to sure. Yeah. We work on it.
Thank you,
So
brothers.
thank you
Thank
very
you.
much for being responsive with me also. You really did well in this session.
Thank you, Prathamesh, for your time.
Oh yes.
Now I
Bye
will
guys.
stop the recording.
Huh?